So let's get started. Welcome everyone to the morning session on computational complexity. The first talk is on multipass memory lower bounds for learning problems, and the talk will be given by Shanli.
Hello everyone, this is Qianli. Today I want to share my work about multipass streaming lower bounds on learning problems. And this is the work joined with Shuo Wang from IT and Jiapeng Zhang from USA. And the work is motivated by the fact that if we want to train a big model on hero data, then the training algorithm usually runs in a streaming fashion. So we can imagine that there is a stream of ID training examples, x1 to xn, and the streaming algorithm can scan the whole data one pass or several passes. And finally, it is required to output a hypothesis function in a given hypothesis class, H. And the point here is that the space of the streaming algorithm is bounded. So the streaming algorithm have not sufficient space to store the whole data. And here, our goal is to understand the space complexity of the streaming algorithm. And it may depend on several parameters, namely the data dimension D, and the size of the concept class H, kappa, and the number of examples N, and the number of passes L. Yeah. In a previous co-paper, Brown, and Smith, however, they studied this topic in the one-pass setting. And they proved that for several hypothesis classes, such as neural network regression, and they prove that any one-pass streaming algorithm needs at least d kappa square over n bits of space to learn this concept class. Note that the kappa here is actually the sample sample capacity when the space is unbounded. Yeah, so we can see that if n equals kappa, then this bound is tight, since the algorithm have enough space to store the whole data. Okay. And they further conduct that a similar low bound also holds in the multi-pass setting. And the main contribution of this work is we prove this conjecture. And specifically, we prove that if L passes are allowed, then the low bounds can be divided by L factor. Okay, and so our result implies that first, if we allow multiple passes, then the space complexity cannot be significantly cut. And the second suggestion is that our paper implies that a stream of L times n flash examples is at least as useful as L passes over n examples. Yeah. And here is the proof structure. Our proof uses a three-stage reduction. And the first use a reduction as in the co-paper, we use these learning problems as an embedded mixture of k-independent subproblems. Meaning that there are k-independent subproblems are crowded into one data stream. And then where multipass information cost and is direct sum property, and we only need to show the hardness for the one single subproblems. And then by a similar reduction as in the co-paper, we can reduce this subproblem into a very basic problem called the bit bias problem. And in this problem, we want to distinguish whether a stream of IID random coins are p-biased coins or q-biased coins. And then we prove information cost in the communication setting, and which further implies the low bounds in the streaming setting. As we mentioned, our paper relies on multipass information cost setting, and here is the definition of the notion. This notion is introduced by Stoll paper, and here MIJ means that the memory state of the algorithm after processing xi in the JS path. And this notion is proposed to capture the intuition that the streaming algorithm must memorize some specific information about specific examples. Yeah, and this notion has some nice properties. The first is that this nice notion provides low bounds on the space complexity. And then since the notion satisfies a direct sum property, that is, the IC of mixture of k-dependent subproblems is at least the k square times the IC for each. And next, we will talk about our smallest hard task, namely the B-bias problem. Recall that in the B-bias problem, we want to distinguish whether a stream of IID coins are P-bias coins or Q-bias coins. And we first focus on the special case when p equals 0. And here we prove that the IC is at least mean Q minus Q. And the proof idea is that we prove the information cost in the communication setting. In the communication setting, there are n players. And each player holds a bit, xi. And they want to distinguish this xi are p-biased or q-biased. And communication protocol proceeds in rounds, and in each round, each player, one of these players writes a message on the blackboard, and this message can be seen by all the players. And the information cost in the communication setting is defined as the mutual information between these messages and the input x. And by a generalized cut and paste property, and by extending Giraum's technique for proving the AND function, and we can prove the low bounds for the information cost in the communication setting. Yeah. And for the general case, for the general P and Q, our proof idea is that we will the P-biased coins as a mixture of Q-biased coins and 0 biased coins. And then by using the direct sum property of the IC notion, yeah, we can show the lower bounds for the general case. And here is a summary. In the paper, we prove multi-pass ring low bounds for several natural linear problems, and thus prove a conjecture proposed by a co-paper. And our message is that our results suggest that a stream of L times n flash examples is no worse than L passes over n examples. And for the technical part, we believe that all results about the B-biased problem can be applied somewhere. And here is the open problem. Here we care about, here note that in the Euro setting, the training algorithm such as SGD or ADAM usually shuffles the data after each pass. Yeah. So we want to, we are curious about if our low bounds can be extended to this shuffled case. That's all. Thank you.
We have time for a couple of questions.
Is the bit bias problem the same as the coin problem that people call in literature?
You mean the open problem?
Is the bit bias problem just a different name for the coin problem?
Sorry.
The coin problem in literature is also about distinguishing Bernoulli P versus Bernoulli Q.
Yeah.
Maybe it's just called by a different name as well, so maybe something to look into.
Sorry for my English.
That's all right.
Yeah. Okay.
Other questions? Okay, now let's thank the speaker again. Okay, so the next talk is on low coordinate degree algorithms, part 2, categorical signals and generalized stochastic block models, and the talk will be given by Tim Kunitsky.
Okay, great. So thanks for the opportunity to present here. And yeah, so I'll be telling you about some progress on analyzing so starting out from low degree polynomials and kind of a generalization of those algorithms. So the kind of broad class of problem that I'll be talking about, and I'll give a specific example in a second, but it's about hypothesis testing problems in high dimension. So about trying to distinguish between one of two sequences of distributions on Rn for n growing, one kind of unstructured or null, right, and the other having some kind of special structure. So my notion of kind of succeeding in doing this will be whether you can hypothesis test. So a test is a function that takes a sample from one of these two things and tells you which distribution it thinks it came from. And I'll say that the test is successful if kind of both types of error go to zero, right? The probability that I drew from one distribution, but that actually my test told me it thinks the sample came from the other. So I'll call this property strong detection or just detection, and the question I'll focus on is when do such tests exist for a given sequence of distributions that are computable in polynomial time in n in the problem size. So there's another notion that some of these results will be formulated in terms of, which is about real valued functions rather than these kind of symbolic tests, separating two distributions. So this is the notion of the means, the difference between the means of the two functions under either distribution being bigger than the standard deviation under either in kind of a diverging way. And what is pretty easy to show is that this is actually the same. If you don't kind of have any restriction of the class of functions, this is the same as detection, and actually the kind of equivalence maintains the runtime. So if there is a sequence of detecting tests, then you can just look at the indicator functions, and those will separate these two distributions. And conversely, if you have these separating statistics, you can put a threshold between their average values, and then it'll kind of concentrate enough around the means that that will be a successful test. So the concrete example that I'll be motivated by is the stochastic block model. Right? So probably lots of people have seen this, but this is a distribution over graphs, right? So there's some underlying number n of nodes, and then we'll be observing kind of n choose too many things. And under the null model, we'll just draw these kind of as IID Bernoulli variables, so an Erdős-Rényi graph with some edge probability. And under the structured model, I'll first draw a label, so one of k labels for every node. Right? And then if the labels agree, then the nodes will connect with some one probability A, and if they don't agree, then they'll connect with some other probability B. And so this was studied for a long time, but in particular in this kind of scaling regime, this conjecture came out of the physics literature, that there is this summary parameter, kind of an effective signal-to-noise parameter that is some measurement of how far apart A and B are, right? So how much signal there is in this model. And if this is below some threshold, so kind of scaled this way below 1, then the conjecture is that no polynomial time algorithm should be able to distinguish, to detect between these two distributions in the sense I just said. This is this so-called Keston-Stigum threshold, so I won't kind of say anything about where that name comes from, but I'll use the abbreviation KS for this type of threshold more generally. And so this is a statement, right, about kind of computational complexity, saying that polynomial time algorithms for something don't exist. So this is hard to show unconditionally, but one form of evidence that we have for this is that when we're in this particular regime, then low-degree polynomials of this graph, of the kind of set of entries of the adjacency matrix, if you want, can achieve this separation criterion that I was saying before, right, until they have very, very high degrees. So degree n polynomials can, of course, express any function, degree, I guess, capital N could express any function. And so, right, so you need kind of quite close to that in order to be able to separate the two distributions. So, okay, let me briefly say here, so this was shown in some kind of early work in weaker versions on low degree polynomials, and then in some work that I participated in a little bit later, right, we showed this particular degree bound. So I want to talk about proving similar statements, but for a much more sort of general model of the same type of thing. So first of all, we'll generalize this to kind of arbitrary p-way interactions. So every group of p nodes will interact somehow. And under the null model, they'll just kind of generate IID observations from some one distribution. And under the planted model, we'll give them labels, and then they will interact according to their labels. But now these interactions can be measures on just any sets you want whatsoever, right? So they can carry any kind of information. So for example, if you want to recreate this stochastic block model with just two communities, you would set p equals 2, you would set the observations to be binary, and then you would just set up these measures in exactly the way that we had before. right? But if you take p bigger than 2, then you'll get so-called hypergraph stochastic block models. And if you take this set bigger, and so you can take it infinite or uncountable or whatever you want, then the edges of this graph can carry various information. So people sometimes call these labeled stochastic block models. So now, if you have this big kind of non-numerical set omega, right, then polynomials of it don't necessarily make sense. And so the proxy that I use to kind of for polynomials is these functions of low coordinate degree, which are just arbitrary linear combinations of functions of small subsets of indices of some vector. So if these individual components had to be monomials, these would just be low degree polynomials. But for example, this can express coordinate decision trees where you look at a coordinate, you decide to look at some other coordinate, and et cetera. And if you don't look at too many, you can expand it in this form. And on the hypercube, this is exactly the same notion as degree you can show. But otherwise, it gives some generalization of polynomials to these general kind of product domains. And in particular, so I won't say very much about the proofs, but the main proof technique for the result I was saying before is some kind of Boolean Fourier analysis, decomposition of a polynomial. And here, there turns out to be an analog of Boolean Fourier analysis for arbitrary product measures on any domain, and that's the main technique for what I'll tell you about. So the main result is this kind of condition that shows that low coordinate degree functions cannot separate two distributions. So don't read it, but just kind of touch it with your eyes. And so there is some kind of expectation over a multinomial random vector. There's some sort of scalar random variable, and we say if this is bounded, right, then we have this kind of lower bound. So now you don't read even more than before. So this T is some tensor. It's some object of fixed size. And it involves these parameters of the model, these measures, and it somehow kind of summarizes the effective noisiness or the amount of signal carried by the model. It's kind of like the role that A minus B played before. And in particular, you can see that if you look on the sort of diagonal of this tensor, what you get is the chi-squared divergences between the measures appearing in the planted distribution and the one appearing in the null distribution. So in some sense, this is measuring this kind of distance. So the reason that this is nice is that we now only care about studying this particular random scalar variable rather than this entire big high-dimensional statistics problem. And really, at the end of the day, only this multinomial random vector. So really, it kind of suffices to, so a slightly less naive version of just this type of bound by the norm of this tensor and the norm of this multinomial random vector, actually after this kind of decomposition into the mean and the fluctuations. So let me just quickly mention two applications. So first of all, you can set up a sort of hypergraph version of exactly the same model that I mentioned before, where now just groups of P nodes interact. They each have a label, and if they're all in the same community, then they interact one way, and if not, then in another way. So there's a corresponding conjecture from the physics literature about exactly the same kind of Keston-Stigum threshold below which it's conjectured that no polynomial time algorithm can detect. And using this type of criterion, with very straightforward calculations, we can show that no low coordinate degree functions, which because this is a Boolean problem are the same as low degree polynomials, can separate these two distributions. Now for another application, I'll talk quickly about a problem over groups. So here I'll observe sort of a graph or a matrix worth of observations. It'll either be just drawn uniformly from a finite group, or the indices will be associated to group elements, and I'll observe group differences with some kind of noise, with them replaced at random with just uniform elements from the group with some probability. So again, it was conjectured that if this probability is too small, if I have too few correct observations, then it's hard to detect this kind of structure. And it turns out that in some cases, this matches the performance of some simple algorithms. What we can show, again, is that below this threshold, you need very high coordinate degree in order to separate. And let me just mention that here, really, to formulate this nicely, you do need this notion of a coordinate degree. So let me not go into any further details, and thanks for your time.
We have time for a question or two.
Thanks for the talk. Do the groups in the setting you mentioned in the end need to be abelian for your Fourier analysis to go through, or any group is fine?
No, any finite group. And so this thing I mentioned about the spectral algorithm, that so the simplest algorithm is for abelian groups, where you just kind of embed into complex numbers, into roots of unity, and just think of it as a spiked matrix model, as kind of a PCA problem. But then for non-abelian finite groups, you can do some kind of message passing type of algorithm involving like irreducible representations, and so that is conjectured to achieve the same threshold as well. Yeah.
Thank you.
Any other questions? No, just thank the speaker again. So the next talk is on algorithms for sparse learning parities with noise and LSPN against low noise. And the talk is will be given by Wenchuan Xu.
Hi everyone, I'm Wenxue, and today I will be presenting our work titled Algorithms for Sparse LSPN and LSPN Against the Low Noise. The joint work with Xue and Zhai Enhe. First, let me introduce learning parity with noise. In this problem, we are giving x in f2 m times n. In this talk, we use m to denote the number of samples and n to denote the dimension of LPN problem. We use xi to denote the ith row of x. There is a hidden secret, and noise ID noise of rate eta less than 1 over square root of n. Y is corrupted by the noise. For example, for the first bit of y, it equals to the inner product of x1 and the secret plus the noise. So our task is to find secret giving xy and this low noise rate less than 1 over square root of n. The best algorithm in this low noise region is Gaussian elimination of e to the o eta n time with on samples. For the noiseless setting, you can just solve the linear systems where Gaussian elimination very fast. But for the low noise setting, you can also expect that you get n noiseless samples, which spans the whole space. Then you can still use the Gaussian elimination. The probability of you can find these n samples is e to the minus eta n. So you need to repeat e to the o eta n time to blow up the success probability. We mainly focus on the sparse variants of LPN. In this work, we usually use k to denote the sparsity. And we say x is k sparse if the Hamming weight of x is k. And we use n choose k to denote all k sparse vectors in F2n. Here is an example of the 3 sparse vector. The first variant is learning sparse parity with noise, or simply LSPN. In this variant, we restrict secret to n choose k. This is a central problem in learning theory. Learning k-home tasks can be reduced to LSPN. The second variant is sparse LPN. This is equivalent to random k-XOR, where each xi is sampled from n choose k, and this is usually used as a fundamental assumption in cryptography. Let us look at our first result for LSPN. Our theory is that for any sparsity k and eta, noise rate eta, we can solve LSPN in time eta n over k to the k and k over eta plus k log n samples. What we want to stress is that our algorithm is simple and easy to implement. Besides, it's faster than the previous algorithms when eta is from k over n to the square root of k over n. Here are some previous results. Okay. Our second result is for sparse LPN. For simplicity, we fix k equals 3 and such that xi is sampled from n choose k. There is this trade-off between time and samples for this problem. When m equals on, we only have Gaussian elimination with time e to the o eta n. And when m is very large, say larger than square root of k of n choose k, which is approximately n to the 1.5 here, a birthday paradox implies an algorithm in Paulian m time. in this case, we can find two vectors xi and xj, which are just the same with high probability by the birthday paradox argument. So the smallest linearly dependent set in this case is 2. And for the last case, the m is it can be say as a geometric mean of the first two cases by the parameter delta. There exists XOR algorithms of time e to the n to the delta. And this because the smallest linearly dependent set is of size n to the delta. Our contribution is an algorithm to solve spatial LPN in time e to the eta n to the 3 plus delta over 4 with the same sample complexity as the third case. This picture shows a comparison of our work to the previous results. The x-axis is for noise rate, eta equals to n to the x minus 1. And the y-axis is time, t equals to exponential n to the y. When y is 0, we say the time is polytime. And when y is 1, this is just the exponential time. When the noise rate is less than n to the minus 0.6, our algorithm is faster than the previous results. And when eta is less than n to the minus 0.8, our algorithm just performs similarly as the concurrent work by Dao et al. The key insight of our work is that both problems, LSPN and spatial LPN, can be solved by an unified framework based on domain reduction. This is widely used in spatial recovery and compressed sensing. However, there are classical methods that don't apply to LPN directly. So here's our idea. We have our domain reduction has 2 steps. The first is to sample a subset to reduce the original problems into sub-problems. Then we solve the sub-problems by some algorithms. But note that for the low-noise region, Gaussian elimination is the only known algorithm for us. So we just use the Gaussian elimination here. Our algorithm, our framework makes the algorithm easy to implement and space efficient. Besides, it shows somehow a conceptual connection between the 2 sparse variants. Let me give the algorithm sketch for sparse LPN as an example. Recall that for sparse LPN, each xi is sampled from n choose k, and we let k equals 3 and m equals n to the 1.4 here. Our domain reduction has 2 steps. The first step, we partition n into the 0.8 blocks. Each block has size n to the 0.8. Then for each block, for each I, we use Si to denote all the samples whose support falls entirely in II. Then we solve the sub-problems by Gaussian elimination over Si. This picture shows somehow a process of our domain reduction. The key step of analysis is to make sure there are enough samples to in Si so that we can apply Gaussian elimination in time e to the O eta n to the 0.8. Okay, to conclude, we provide an unified framework for both LSPN and sparse LPN, which improves both of the problems for some range of parameters. And here are many interesting future directions. The first is, can we find more application of our framework? Second is, the key of sparse LPN is to find a linearly dependent set. For example, for k equals 3 and m equals n to the 1.4. Figure and Shai can prove that the smallest linearly dependent set is always of size n to the 0.2. And they can find it by, in time, exponential n to the 0.2. So in our algorithm, we actually find a linearly dependent set of size n to the 0.8 in time polyon. So we are interested in the trade-off between the size we can find and the time. The third is the Applebaum et al. Conjectured for k equals 3 and m equals n to the 1.4. The time complexity of sparse LPN is exponential omega eta n to the 0.2. So it's still open. that is exponential is the time of exponential eta n to the 0.2 possible. Recall that our time is exponential eta n to the 0.8. Okay, thank you very much for listening. Any questions?
Questions? Yeah, I guess I have a question. So I was wondering if in the constant noise regime, does it give any even very modest improvements over this Blum-Kalai-Wasserman result?
Yeah. In constant noise regime, we can our framework can combine with the BKW algorithm, which can also improve for slightly low range of parameters.
Oh, okay.
Yeah.
Okay. Any other questions? Okay. No, let's thank the speaker again. Hi, the slide is not advancing. Oh, now it's working.
Oh,
Okay. So the next talk is on computational equivalence of the spike covariance and spike Wigner models via Gram-Schmidt perturbation, and the talk will be given by Alina Harbuzova.
Hello, everyone. I'm here to present our work with my PhD advisor, Professor Guy Bressler, on the computational equivalence of two statistical models. So why should you care about computational equivalence? The motivation actually comes from the success of the worst-case complexity theory, where the problems of interest are classified into computational equivalence classes, such as, for example, a class of NP-complete problems. For the modern average case problems, where the input is random, such classification and any kind of equivalences are currently missing from the literature. So we address this by establishing first computational equivalence between two very well-known problems of high-dimensional statistics, spike covariance and spike Wigner model. So how do we approach this question of establishing equivalence between statistical models? The main tool at our disposal is going to be average case reductions. Many average case reductions are known. For example, on this diagram, you can see plenty of the reductions stemming from the planted clique conjecture. Average case reduction is an efficient algorithm that takes an instance of a statistical problem, like planted clique, and maps it to an instance of a different statistical problem while preserving the distribution. Then conjecture the hardness of the former one, we obtain the hardness of the latter one. As you can see from this diagram already, most average case reductions that are known are one-way reductions, so from the conjecture to other problems of interest, and there are no two-way reductions or equivalences between problems. Work on equivalences, prior work on equivalence largely focused on the problems that have same structure but maybe different noise distributions or remained in slightly artificial settings. Our work establishes the first computational equivalence between two well-known problems, which actually appear here on this diagram under slightly different names. So let me define the models that we're going to consider. We consider the sparse variance of the two statistical models, where the signal is represented by a d-dimensional vector u that has k non-zero coordinates, and the values of the non-zero coordinates are of approximately the same size. Under the spike Wigner model, we observe a random D by D matrix that has a rank 1 signal UU transpose multiplied by the signal-to-noise ratio lambda plus additive Gaussian noise W. This random model has natural associated detection and recovery problems to it. Detection is to distinguish between this distribution and the pure noise W, and the goal of recovery is to estimate the underlying vector U. The second model is the sparse spike covariance model, where we have the rank 1 signal UU transpose in the covariance of the following Gaussian distribution, from which we draw n IID samples. If we arrange the samples in the columns of the D by N matrix, we have a very convenient representation. The signal is contained in the k rows corresponding to the non-zero entries of the signal vector U, plus additive Gaussian noise independent of the signal. Since the signal for this model is contained in the covariance of this Gaussian, it is very natural to consider the empirical covariance matrix. And we will indeed look at that. We will look at the empirical covariance matrix, renormalized so that every entry has variance 1. This corresponds to this formula below the second diagram. We can see that once we consider the empirical covariance matrix, we have the rank 1 signal UU transpose pop up here. Let us compare the two statistical models that we have. Recall that Spike-Wigner is a D by D random matrix with rank 1 signal plus Gaussian noise. And once we take the empirical covariance matrix for spike covariance, we also have this D by D matrix with a slightly more complicated structure. So how do we compare the statistical models? Let's start from the basics. Let's compare their expectation. It's not hard to see that under some parameter rescaling, these two models actually have the same expectation, the signal, rank 1 signal, UU transpose, multiplied by the coefficients, lambda for Spike-Wigner and theta root n for spike covariance. Here we emphasize that the noise distributions for the two models are dramatically different. For Spike-Wigner, we have IID noise on our matrix, and for spike covariance, we have Wishart distribution XX transpose, and also these cross terms in the key columns and rows. And this structural difference of the two models is the main challenge in relating them in some sense and establishing average case reductions. Because imagine, like, an average case reduction is supposed to take as an input an instance of spike covariance model, this correlated thing, somehow with an algorithm efficiently decorrelate it and map it to the Spike-Wigner model. This is indeed what our reduction achieves with a very non-trivial algorithm. Before I describe that, let me actually discuss what it means to establish computational equivalence for statistical models that have all these parameters and hardness regions. For that, I present the phase diagrams of the two models. For the Spike-Wigner model, let's parameterize the phase diagram by the sparsity k against the signal-to-noise ratio lambda, expressed as the powers of the dimension d. For the spike covariance model, we fix the number of samples n in relation to the dimension and parameterize it similarly. So now every point on the phase diagram corresponds to a certain parameter regime of the model and of the associated detection and recovery problems. We say that this point belongs to an easy regime, denoted as green here, if there is an efficient algorithm. We say it belongs to the impossible regime if we have information theoretic lower bound. For both of these problems, it just so happens that the phase diagrams for detection and recovery coincide. Both Spike-Wigner and spike covariance exhibit the computational statistical gap, meaning that there is this remaining blue area where we say it's a conjectured hard regime for the two problems. Even though separate lines of work obtain these diagrams, so establish these efficient algorithms and lower bounds, it is hard to miss that the shapes of the diagrams are very similar up to just some parameter rescaling between them. And this parameter rescaling is the one we noticed before when we compared the expectation of the two distributions. So what does it mean to establish computational equivalence between problems? Since our goal is to show that these phase diagrams are not just coincidentally similar, but there's some fundamental phenomena informing them, the strongest notion of equivalence we're going to aim for is the bijective computational equivalence, meaning that with this natural one-to-one map between the phase diagrams, we have average case reductions both ways. If you don't like thinking about phase diagrams, just remember the picture with the two D by D matrices. The goal is to build algorithms mapping one into the other. To slightly relax the definition, we also consider the phase diagram equivalence, where what's required is a surjective map both ways, meaning that knowing hardness for the entire region of one problem, we obtain hardness for the entire region of the other. With those definitions in mind, let me present our results. We note that there exist average case reductions from the Spike-Wigner model, this is the one with the IID noise, to the spike covariance. And we were in fact obtained to get a computational hardness result for spike covariance for parts of parameter regime for spike covariance. Our contribution comes from the first reduction in the opposite direction, the algorithm that takes the correlated instance of the spike covariance model and maps it to the Spike-Wigner model. Our reduction uses as a subroutine, 'n' 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 'n Combined with the known reductions, we obtain several equivalence results, both bijective and phase diagram equivalence, for a large part of their parameter regimes of these two statistical problems. In particular, for the number of samples of spike covariance larger than dimension cubed or equal to the dimension, we obtain certain equivalence results. We know that our reduction actually works in the interim regime that is not covered in this theorem when number of samples is between d and d cubed. So any improvement to the spike-Wigner to spike covariance direction would immediately yield new equivalence results when combined with our reduction. This is, of course, the active area of our research. To summarize, we established the first computational equivalence between two really well-known models of high-dimensional statistics, spike covariance and spike-Wigner model. And we keep in mind this bigger goal of classifying the problems of interest, like the two we considered, into computational equivalence classes. Such classification is largely missing from the average case complexity literature. We hope that the subroutines that we used in our average case reductions will find future applications to new average case reductions in the field. Thank you.
We have time for a couple of questions.
Can you say about like how do you do the Gram-Schmidt orthogonalization? Like what, like which vectors do you orthogonalize? And I had another question. Is it like generalizable to more noises? Like which noises can be reduced from one to another?
Mm-hmm. Yeah. Okay, let me quickly summarize where the Gram-Schmidt orthogonalization comes in play. We consider the samples of spike covariance, we consider the rows of this D by N matrix, and we apply Gram-Schmidt orthogonalization to that, showing that actually, even though it's like an evolved algorithm, it preserves the signal in the way you would expect. And then somehow we leverage the Gaussian rotational invariance to show that you can use that result to obtain IID samples from the spike-Wigner. About generalizing to other distributions, I guess we did use a lot of properties of Gaussian distribution, but it seems maybe if there is some measure with rotational invariance, it might also work. I guess, have to see.
Yeah, so in the statement of the result, the scaling d cubed played this special role. So is that related to how the null models become indistinguishable? And so is that good? Is it like easier to do this argument when the null models are indistinguishable, or is it harder? Or
Yeah. Thank you for pointing that out. In fact, when n is larger than d cubed, it's a known result by Babak et al. That the null models of the problems are indistinguishable in total variation. And in fact, it does help. There is still technical work remaining, in particular because, let me show the diagram, because of these cross terms. So the spike covariance matrix is still quite different, and we do prove a result that removes those cross terms in total variation. So it becomes easier. In fact, you don't need to do an active algorithm per se, but you still have to prove some stuff.
Well, I have a question too. So have you thought about generalizing this when you have more than one principal component, like more than one sparse principal component, like you have a subspace which only has sparse vectors? Can you extend those ideas, you think?
Yeah, it's a great question. It's definitely something that crossed our minds. The perturbation result that we proved is quite involved with one vector already, so it would require quite a lot of additional technical struggle, I guess, to obtain that. Yeah, I guess that's all.
Any other questions? If not, let's thank the speaker again. To advance the slide.
Okay. I have my own laser.
Oh, but oh yeah, okay.
That's okay. I just use it to.
Oh yeah, okay. So the next talk is on some easy optimization problems have the overlap gap property. And the talk is going to be given by Shuangping Li.
Yeah, thank you so much for the introduction, and thank you everybody for coming. So this is me in a nice suit, and this is my collaborator Sliu in a very casual outfit. So today I'm gonna talk about, I mean, everybody is going fast, so it seems that we have at least half an hour in the session, so I might go a bit slower. So I'm gonna talk about some easy optimization problem have the overlap gap property. Essentially, so the sort of the topic, it's summarized in the title. So sort of the first half of the sentence is more easy to understand. So by easy, I just mean polynomial time. So this is really, there are some polynomial time optimization algorithm that have the overlap gap property. But what exactly is the overlap gap property? We probably needs a little bit more motivation to it. So. Okay, so let's consider a motivating example, which is, say you have an Erdos-Schwenk graph with n vertices and the edge connecting probability is a half, and you want to look for the largest clique. So the largest clique is not very hard to show that it is of size 2 log n. And then a very simple greedy algorithm finds a clique half the size, which is of size log n. And then because it's too simple, in 1976, Karp challenged to find a better algorithm. So is there a better polynomial time algorithm that can go beyond log n? And then this is still an open problem up to today. And people even start to think that maybe there's no polynomial time algorithm that can go beyond log n. Okay, so this is the kind of phenomenon that we see in previous talks, that there's gaps between computations and statistical limit. And in fact, this is not just subject to this largest clique problem. There's a whole list of problems that has a similar phenomenon, that there is a gap between the optimum value C star and C og, which is a value that the best known polynomial time algorithm achieves. For example, there's, I mean, you don't have to take pictures. There's a very nice survey by David Garmarnik and everything it's there. So for example, there's the largest independent set problem. There's also a lot of more statistical flavored problem, also the binary, my favorite binary perceptron problem. Okay, so now whenever we have this gap between the optimum value and the algorithm, we think, what is the barrier that prevents algorithms from going beyond this C-og? One of the most popular or famous property that people look into is the overlap gap property. So I'm going to define to you what is the overlap gap property and explain a few perspectives on why overlap gap property is very successful. So essentially, this is just saying that if you look at approximate optimal solutions or near optimal solutions, they form some clusters. So the OGP is originated from some study in statistical physics, and here's the definition. Suppose, and pretty much the only technical part in the slide, so suppose that we look at an optimization problem with a loss function, and then there's some random input Kasi. Think of Kasi as, for example, the random graph in the largest clique, or some Gaussian random matrices in spin glass problems. Okay? And then suppose your sigma 1 and sigma 2 are approximate optimal solutions. Then what OGP says is that the distance of sigma 1 and sigma 2 are either small or large. In other words, there's a gap between their distances, which in the physics term means that their overlap has a gap. So this is also where the name overlap gap property comes from. Okay, so essentially it just says that two near optimal solutions are either close or far. Here is a better picture. Suppose this is your loss function, and this is a global minimizer. And now let's look at the mu approximate optimizers. So for example, solutions here, and solutions here. And they're indeed clustered. So sort of vertices are either, so solutions are either close here or far away here. This is essentially what the OGP says. So this is actually not the most vanilla version of the overlap gap property. There's a lot of fancier version. One of them is the ensemble OGP. I want to put the slides here because ensemble is French, but otherwise I'm going to skip the slides. Essentially, ensemble OGP just says that if you have like correlated random instances, then this is what this describes. And then there's also some technical term called the chaos event that you also want the property to satisfy. Okay, so why is OGP successful? There are two reasons. One reason is that rigorously, OGP can be used to provide unconditional lower bounds against the stable algorithms. What is a stable algorithm? It just means that if you change your input a little bit, the output also just changes a little bit. If this is a not randomized algorithm, say a deterministic algorithm, it just means that the function is Lipschitz. Okay, so there's a lot of algorithms that are known to be stable in different situations, like Langevin dynamics, approximate message passing with an O1 number of iterations, and so on. So I want to use one slide to tell you why, if you have OGP, this indicates that there's going to be hardness for stable algorithm. And the proof is actually just by picture, so we can take a look. So assume by contradiction that we have the OGP for the problem, but there's also a stable algorithm that finds approximate optimizers. Okay, so let's start with two faraway inputs, CC0 and CC put them through algorithms. These are A of CC0 and A of CC. This is something that I skipped for the chaos event. The chaos event guarantees that these 2 points are far away. Okay, so A of CC0 and A of CC are far away. Now let's interpolate between these random inputs, CC0 and CC to have like CC1, CC2, all the way to CC. Each time I just change a little bit. Okay, now the overlap gap property, or the ensemble overlap gap property, says that if you look at the distance of this output to so this A of CC0 is an approximate optimal solution, the distance is either very small or very large, right? Very small means that you are sort of here, the distance is below mu1, and distance large means that you are here above mu2. So sort of it means that you're like doing this, and there's going to be one step that you're going to jump through this big gap. And if you jump through this big gap, this means that your algorithm is not stable anymore. So this contradicts the fact that you are actually making little changes at each step. Okay, so this becomes a standard. So whenever you sort of see that there's OGP phenomenon that goes on in your model, then this implies that stable algorithm fails, or there's hardness for stable algorithms. Okay, so this is one of the reasons that OGP is useful. And another is that actually in a lot of these models, for example, in our motivating example, the largest clique, you see that where you sort of want to understand why we can't really go beyond log n, it's because whenever you go beyond log n, there's OGP. Or in other words, sort of OGP provides a good indication for the current phase diagram for hardness. So, and this is not only just for the largest, the clique problem. There's a lot of these models here. This is again in David Gamernick's survey. So in many such average case optimization problems, the overlap gap property kicks in at known computation threshold. So in other words, whenever you observe some kind of or some format of OGP, this seems to coincide with the phase of hardness. Okay, and then this makes people to think that is it really the case where there's a meta conjecture in the field that says that unless a problem has certain algebraic structure like KXOR or something that can be solved by Gaussian elimination, then stable algorithms capture what is possible in polynomial time. Okay, so what we are doing is essentially just says that no, the meta conjecture is not true. So we provide sort of an example or a counterexample to this meta conjecture. So we show that the shortest ST path problem, this is a pretty well-known problem, has the overlap gap property in the following two sparse graph models. The following two models. One is the sparse Erdo-Schrödinger graph with edge connecting probability b log n over n with b larger than 1. This just guarantees that the graph is connected with high probability. And then secondly, or a complete graph with ID exponential edge weights. It doesn't actually have to be exponential. It could be any of your favorite positive distribution. Exponential is a little bit convenient, but it could be more arbitrary this way. Okay, so note that the shortest SD path problem is polynomial time, by your favorite shortest path algorithm. So this constitutes the first example in which the overlap gap property is not predictive of algorithmic intractability for a non-algebraic average case optimization problem. Okay. So essentially, the OGP says that sort of if you look at the approximate shortest path between S and T, they either have a little overlap here or a lot of overlap, and they can't have intermediate overlaps. Okay, so I think I only have 1 minute left, but since our session can go all the way, so I'm going to explain a little bit more. So here's a little bit more precise result. So I don't want to read the theorem, but essentially you're like the overlap is either very small or one completely overlap. Okay, so I'm going to explain a little bit of the proof ideas, which is very straightforward. What does it mean to have an overlap gap? Which means that your overlap has a gap, right? In other words, the overlap of the two paths is like having an intermediate overlap. If you have an intermediate overlap of two paths, then it means that they form a cycle. And this is not just some weird cycle. It's a cycle sort of in neighborhood of your source S. And in sparse graphs, it's not very likely to see this. And you can just show that this is not very likely to see through a first moment computation. So the proof is not very hard. The hard part I deleted, so the remaining should be more straightforward. Okay, and if you don't feel like the sparse model, sometimes people say that sparse models can be weird. There's also a version of the dense model, which is that if I have a complete graph, which means that there's a connected, all the edges are there, with an ID exponential one edge weights, then a similar phenomenon holds, so the overlap is either very small or completely overlapped. And here, how do you prove such a result? So it sounds very hard, but it's actually very similar to the sparse graph argument. Because one can actually show, this is textbook proof, that the shortest path in this weighted complete graph has weight that's approximately log n over n. So if the shortest path already has weight very small, then it means that if you have an edge with weight more than log n over n, then it wouldn't really qualify to be in the shortest path. So then you can just restrict yourself to all of the edges with a very small edge weight. Then this reduces to a sparse model again. So this is just the sparse model, and then you show that I can't have an intermediate short cycle in the neighborhood of S, so there's OGP. Okay, so let's have a quick summary. So we showed that, so it is known that OGP is known to give lower bounds against the stable algorithms rigorously, and OGP kicks in at known computation thresholds for many average case optimization problems. Here we show that the shortest SD path problem has OGP in the sparse early training graph and complete graph with ID exponential weights. And this constitutes the first example in which OGP is not predictive of algorithmic intractability for average case optimization problems. So I'm going to spend and we also have some results on low-degree polynomials and sampling, but feel free to read the full version of the paper. Okay, so there's just one last slide on future directions or questions. So it would be nice to come up with some other examples or classes of algorithms that's sort of in the same flavor, that OGP does not match known algorithms. Now we can think of something that's either very arbitrary or very artificial, or it's very similar to the example that we have here. Something that's very different would be appreciated so that we can see what are some common features and then maybe develop a general theorem out of it. So in doing it, you might sort of try to think, what is special about this example? Why is this shortest path example successful, right? So there could be a few reasons. One of them is that actually, if you look at the size of the shortest path, it's sort of on the size of log n, which is not polynomial time, which is not polynomial in n, right? Or it could be that being a path means a very rigid constraint. So if one of these edges is not in your graph, then this is not a path anymore. Or it could be that the path has some kind of recurrence structure. So maybe some of these could be helpful in finding the solution. Okay, so this is the last slide. So now we know that OGP is a good sense of whether stable algorithms are hard or not, but just looking at stable algorithms aren't enough. Whether there's a more appropriate sense of hardness for other classes of algorithms like linear programs or semi-definite programs would be a great future direction to think about. Okay, so that's all. Thank you so much, everyone.
As Shuangqing pointed out, there's a lot of time for questions. So.
Yeah, thanks for the talk. I guess in your proof that, or the heuristic for why problems with overlap gap property are hard, were that like it had to jump this sort of barrier. I guess what goes wrong with that sort of argument in the shortest path setting?
So I think because these algorithms use the sort of the recurrent structure, for example, it doesn't, so it's not really in this graph distance sense, where the path is very fragile in the sense that if one edge is broken, it's not a path anymore. But actually, the algorithm explores the structure in some other ways. Yeah, that's a great point. Yeah.
Thanks.
Yeah.
Can I just, or I guess?
Yeah, it's recorded, so it's good to.
So do you, I think there's some kind of like weaker version of this in your paper, but do you think that you can kind of massage this type of example into a counterexample to this low degree polynomials conjecture in its official version?
I don't think so, because there are some polynomial, like low degree polynomial of degree like log n over log n that computes the shortest path. So the degree is very small. So we can show that, for example, big constant degree polynomials wouldn't really success. And I think the actual transition might happen at degree log n over log n. So it's like maybe too small to.
I see, but like, do you think some kind of similar-ish problem might be able to do
Could
this?
be, yeah, could be.
Other questions? I guess a similar question to maybe, yeah, here you're using this connectivity structure, which is very global.
Yeah.
And it's also very combinatorial in some sense. So
right.
I was wondering if there are maybe, real like points in space, style geometric problems where you think, there could be such a.
So that's a great point. So for example, if you are just like, I just threw some points in the two-dimensional space and connect them if they're close or something and look for shortest path, this doesn't work. This doesn't has OGP. Yeah, so it can't be the low-dimensional situation. Even just the lattice. I look at first passage percolation on the two-dimensional lattice. It doesn't work. It doesn't have OGP. Yeah, so yeah, it's weird. So, but if it's hypercube, then it works. Yeah, so the dimension needs to be high, which means that actually the shortest path is very small compared to the size of the system. I don't know whether that's an important feature here. Yeah.
Okay. Any other questions? Okay. If not, let's thank the speaker, and we'll thank all the speakers in the session. We are done with the session, and we have the keynote talk at 11:30 in the auditorium.